Greeting guys. So welcome back. So in this video we will be seeing how to fine-tune YOLOv10 model for object detection purpose. So YOLOv10 was released on 23rd May this year. So it's a real-time object detection model developed by researchers from Tsinghua University. So YOLOv10 represents the state of art in object detection, achieving lower latency than previous YOLO-based models with fewer parameters. So in terms of performance, the YOLOv10 paper notes that YOLOv10 is 1.8 times faster than RTDTR under the similar average precision on COCO with 2.8 times smaller number of parameters and flops. So compared with YOLOv9, YOLOv10 has 46% less latency and 25% fewer parameters for the same performance. So let's see in details of its architecture and hands-on lab to see how to fine-tune it with custom dataset for detection tasks. So we will be fine-tuning to detect cancer cells which help in diagnosing lung cancer. So let's dive in. We're gonna see what is the backbone of YOLOv10 and also we will be discussing how we can fine-tune the model using YOLOv10 using a custom dataset. So YOLOv10, which is built on the Ultralytics Python package by the researchers from Tsinghua University, as I said, which introduces a new approach to real-time object detection, addressing both the post-processing and then model architecture deficiencies which are found in the previous YOLO versions. So by eliminating non-maximal suppression, which is NMS, and optimizing various model components, and YOLOv10 have achieved state-of-art performance with significantly reduced the computational overhead. And then extensive experiments demonstrate its superior accuracy, latency, and also trade-off across multiple model scales. So real-time object detection, which aims to accurately predict the object categories and then positions in the image with low latency. So YOLO series has been at the forefront of this research due to its balance between performance and efficiency. However, if you see reliance on NMS and architectural inefficiencies have hindered the optimal performance. So YOLOv10 addresses these issues by introducing consistent dual assignment for NMS-free training. So if you see architecture of YOLOv10 is built upon the strengths of previous YOLO-based models, while introducing several key innovations. So if you see, the one is backbone, which is responsible for feature extraction. The backbone in YOLOv10 uses an enhanced version of CSP-net, which is cross-stage partial network, to improve the gradient flow and also reduces the computational redundancy. And next component is NIC. The NIC is designed to aggregate the features from different scales and process them to the head. And it includes path aggregation network layer. And another component is one-to-many head. So one-to-many head, which generates multiple predictions per object during training to provide a rich supervised signals and improving the learning accuracy. And another component is one-to-one head, which generates a single best predictions per object during inference to eliminate the needs for NMS, thereby reducing the latency and improve the efficiency, overall. And the key features would be NMS-free training, which uses the consistent dual assignment to eliminate the need for NMS, reducing the inference latency, including lightweight classification head and then spatial channel decoupling and also rank guided block designs. And if you see enhanced model capabilities, also it incorporates large kernel convolutions and partial self-attention modules to improve the performance without significantly increase the computational cost. So YOLOv10, which comes with various model scales now. So one is YOLOv10N, which is nano version, for extremely resource constrained environment, and then YOLOv10 like S, which is small version balancing the speed and accuracy, and the third one is like a YOLOv10M, which is the medium version for general purpose usage, and then YOLOv10B, which is balanced version with increased width for like higher accuracy, and another one is YOLOv10L, which is large version for like high accuracy at the cost of like increased computational resource. And the final one is YOLOv10X, which is extra large version for maximum accuracy and performance. So here you can see the different, the parameters used for the each type of model, and then the comparison as well in terms of latency. And also finally, if you see the experimentation result here, so YOLOv10 has like been extensively tested on like standard benchmark like Coco, demonstrating a superior performance and efficiency. The model achieves like state-of-art result across like different variant, and showcasing the significant improvement in latency and accuracy, which as compared to the previous versions and other contemporary detectors. So compared to other state-of-art detectors, YOLO10S, which is 1.8 times faster than RT-DTR, as I said, and YOLOv10B, which is 25% fewer parameter and 46% lower latency. YOLOv10, which outperforms YOLOv8 based models with good average precision, and then with fewer, 2.3 times like fewer parameters. So this is a basic, introduction about like YOLOv10. Let's do some like hands-on practice how we could fine-tune YOLOv10 object detection model with our custom dataset. So I have already prepared a new notebook here. So where we will be seeing like installing YOLOv10, and then we will be downloading the pre-trained weights for this model, and we will be downloading our data set from Roboflow Universe, and then we will be doing our custom training, and we will be validating the model against the validation set, and then we will also try to explore a bit on like inference and testing with new data. So before diving in, I really would like to show like which data set that we're gonna use from Roboflow for this tutorial purpose, which is like cancel cell detections. So basically we are in the Roboflow Universe website. I will put the link of all the resources that we saw in this tutorial in the description below, so that you could like go and refer for the further learning. Okay, so yeah, so in this dataset, if you try to explore the dataset, so basically we see like we have two different classes, which is major classes. And let me take the train split. Let me display it. So if you see like we have like two classes, one is white blood cell class and another one is cancer cell class. So our goal in this tutorial is to classify these two classes using YOLO model. So we just have already annotated by the National Yang Ming Cho University, and yeah, so it's easy for us to like just grab this data set from the Roboflow repository, and let's connect it here with our collab to download it. Okay, for that you need Roboflow API to be configured. So you can go here to the type on like my project. From here, if you see like you can find in your profile, you can find API key. So from here you can copy your API key. Okay, so this is the key that I have already created earlier for this tutorial, and yeah, I will be using this one. If you don't have one, you have to create for sure an API key from here. Okay, so let me go back to our notebook. So let me check before executing the notebook that we have like NVIDIA which is connected to our notebook. As we are using Google Colab for this purpose, it's already connected with a GPU here, if you see. So let me get the current working directory to just push our data maybe in the later stage and then download the pre-trained YOLOv10 model. So let me install like YOLOv10. So it's their official GitHub repository. So let me go here to this link and yeah, we'll be downloading this. It may take like few minutes to like install. So as we're gonna use like Roboflow dataset, we need to like install Roboflow library, and we will also download supervision to visualize our result. So it's done now. Let's download the pre-trained weight for our YOLOv10 model. So for the simplicity of this tutorial, I have used like YOLOv10 N model, which is the nano model, which is the smallest one which is available. So let me download and put it in my home directory, that is this one. We will be creating like weights folder here, and we will try to put this model in the weight directory. Okay, it's done now. Let me refresh. So if you see here, we have our weights folder which is created, and inside we have downloaded our pre-trained model. So once it's done, I have already access to my API key. As I said, I just copied from from here, from the Roboflow API, and I have already set up my environment variable for Colab. And yeah, so we will be try to access to the Roboflow Universe to download the dataset from this project. From this workspace of this project, Kansas Cell Box. Okay, and we will be downloading it here. As this dataset which have the YOLO v8 model capability, the version of the dataset is which is compatible with YOLO v8, and we will be downloading the same to work with YOLO v10, and it will work fine as well. So let me download the dataset from Roboflow Universe. So what it will do is it will create the dataset directory here in our working directory. So I have like imported my .n file because it says it's missing. Maybe while I was refreshing my session, it was disappeared. So no problem. I have put up my .n file. So there is nothing in my .n file. You just have this variable and with the API key. So let me rerun it to create the dataset folder. So yeah, as it have already created dataset folder here. What it will do is it will try to download the data from the Roboflow Universe to this directory. Okay, great. So let me refresh to see. Yeah, so it have downloaded the project, and if you see inside this project, we have test train valid, which further have image and labels. So it hold all the images. Let me open single image photo. Yeah, to visualize. So we have the label file with annotation. Okay, so with the class and the bounding box coordinates, same which will goes for like training dataset and validation dataset. And another file that we found here is data.yml in the dataset. So basically it holds the information about the dataset and path to the test, train and validation data. So it's done now. So in this line, what we are going to do is we're going to start our custom training. We will be training our model with task detect. We will be using object detection. So we are in training mode, and we will be train our model for 10 epochs, and then we'll be using batch of 32 size, and then we will be getting the plots as well. So these will be like using the model which is from our weight directory, and our dataset locations details are provided here in the data.yml. Okay, so we are ready to run the custom training. Okay, as expected, we are end up with the error. So I think it seems like working fine now, because we have to just already the working directory is attached, so we have to specify the path in a correct way. So I have corrected this as and start the fine tuning process. We should wait a little bit. So it just started the first epoch. Let me close all this. So if you see during the run, it just have created the run directory where we will be just having the data about the training information. This one is our failed run, as we haven't mentioned our directory in a right way. So the run which is going on here is the train 2. You can find this information here, like, so all the information and the result plots are like located here in the train 2. So let's wait a little bit. I will go and have my coffee and come back. So now we are good to go. Like, our training have been completed for 10 epochs. If you see the average precision, like it's improving for each epochs, and our final one is 0.79. Maybe we can also like, train for more epochs that could improve the average precision. Okay, let's explore a bit like wherever like training script is present. As I said, like it's present in the train 2. So we have our confusion matrix. Yeah, so let me grab the confusion matrix and display it. Okay, try to search in the train 2 folder. It's much better. If you see, like we are having like many test prediction which are like works well, and there are some false positive and then false negative, but yeah, still. So let me print the I should rename every time. Yeah, so if you see, our MEP is like improving, and also the precision, it is improving for each epoch. Maybe we can also, as I said, we can try like training it for like more epochs that could improve the model performance for sure. So now it's inference time. Let me grab the like best weight from the train 2 folder, which is saved during the training process. And then what we will do is like we will be calling the supervision detection dataset class for to import the annotation directory path and image path and also the YML. And then finally we will be calling the bounding box annotator object and put it in the variable here, and label annotator from SV and put it here in the label annotator. It will be used for us for the further inference purpose. Let's execute this one. Yeah, so now it's done. So now we will be grabbing the random image from our validation data set. Okay, here, and we will be calling the model. So our model here is the best one that we have saved during, I mean by default it was saved by YOLO. And we will be having our confidence score like really less here. Let me change this to 25 maybe, and try to call the SV detection from analytics and send the result that we get from the model. And we will try to do the bounding box annotation and also label annotation in the image and display the image as the result. Okay, so we see we have like really detected well the cancer cell and then WBC cell. So in this way we can like fine tune the model. Let me try with another image. Yeah, it's super fast now. Yeah, so it can able to like detect the cancer cell and the WBC cell in a good way. Sometimes you see like there are a few overlap between the bounding box, as it have got like detected twice. Maybe the post processing better post processing will like try to clean up these bounding box, I mean the duplicate bounding box, and it will render the result in a convenient way. Yeah. So yeah, that's it for training I mean YOLOv10 model for object detection purpose with our custom data set. Hope you find this video helpful, and I will provide the resources that we have used. Do not forget to subscribe to our channel and like this video if you found it helpful, and let me know in the comment section what topic need to be covered in our future session. Bye. Thanks for watching.